So last time we ended our lecture by having a small discussion on how to calculate an electric field at a point P due to a body or due to a continuous charge of body. So suppose that rather than having a discrete distribution, we have a continuous distribution. So rather than having a discrete distribution, we have a continuous distribution. Then my formula Okay, so then my formula for calculating the electric field will change to integration. In the discrete charges, I was summing over all the charges that made up the system, but when I talk about continuous distribution, I have to take an element and then I have to integrate all over the surface, volume, or line. That is, it depends on how my charges is distributed. If my charge is distributed along a line, then I have to integrate along a line. And if my charge is spread on a surface, and if I know the surface charge density of the medium, then I have to integrate it over the surface. And if I know how the charge is distributed in a volume, then I know rho, that is the volume charge density. Then by knowing the information or by knowing priorly that how the charge is distributed in a volume, I can calculate the field by integrating over the volume by considering the field at a point P due to a small element charge and then integrating it over a volume. So we had a small discussion on it in the last lecture. So to remind you to discuss it, so we will discuss it once again. So suppose that this is my continuous charge medium and I want to calculate a charge at point P. So to calculate the charge at electric field at point P, we have to calculate electric field at point P. So to calculate electric field at point P due to a continuous charge distribution, we have to first consider a, a small charge dq. Okay, so I have to consider a small charge dq, and if this is the separation vector between dq and point P, then suppose this is my origin. So my this is my origin, and this point is the location of the small element charge, that is the source charge. And at this point I have to calculate the field. So r so this is dark r. So at this point rp I have to calculate the field, then my r vector is equal to rp vector minus r res vector. So so you see that's how the position of the source charge and the point at which we have to calculate the field is related if my origin is this. So if I want to calculate the field at point P due to this small charge distribution, so my formula will be E or dE, which is the electric field at point P due to element charge dq. Okay, so if I have to calculate dE, then that will be equal to 1 by 4 pi epsilon naught upon dq upon r vector mod square into r cap. because the direction of the field will be along the r cap vector, that is the separation vector. Okay, so this is the field due to a small element charge dq, and if I want to calculate the electric field due to this whole continuous body, what I have to do is I have to integrate it on the both side. So my dE after integration will change to E vector. This is also a vector quantity. So E vector, and this will be 1 by 4 pi epsilon naught dq upon r square r cap. So to integrate it over the integrate this charge over the over this continuous charge distribution, we have to know how the charge is distributed. So suppose that my charge is distributed along a line. So suppose that if my continuous body is a linear wire that have a lambda, okay. So suppose that if my charge distribution, this continuous charge distribution is distributed along a line. So that means if I have a wire that have a lambda, that is the linear charge density, then I have to replace this dq by lambda dl. Okay, so this formula will be changed to 4 pi epsilon naught upon r square r cap e vector. Okay, so that means this is if my charge is distributed along a line, then my formula will change accordingly, and the integration will take place along a line. Okay, and suppose if my charge is distributed over a surface, then my dq will be replaced by sigma dA, where sigma is the surface charge density and dA is the small element area. Okay, so this is dA, and if I know sigma, then I can calculate the charge in the small dA area. And if my charge is distributed on a volume, so it's a bulk surface. So if my charge is distributed on a volume, then I have to replace my dq with rho dv. Okay, so according to this, my dq with rho dv. So according to how my charge is distributed, my formula will change accordingly. So just solve we will now solve questions on the basis of related to this. So the first question that we will solve is the electric field due to a linear charge density. That means if my charge is distributed along a line, then what is the field at a particular point or the point of interest. So we are given that uh, I have a wire, okay, and the length of the wire is L, and at the end of the wire, so from the end or from the start, uh, at position Z above this point, I have to calculate the electric field at point P, and I know my charge is distributed along a line, so I'm given that my charge density or the linear charge density is lambda. Okay, so this is my linear charge density. Okay, so calculate the electric field at a point P due to this linear charge density or this chart distribution which is distributed along a line, what I will first do is I'll at a distance x I will consider an element of the wire dx. Okay, so the charge dq in this small dx element is lambda dx. So at a point p, the electric field is in this direction. Okay, so this is the direction of the electric field at point P. Okay, so if this is Z and this is X, so this will be under root Z square plus X square. Okay, so we'll substitute that. So my dE is equal to 1 by 4 pi epsilon naught lambda dx, that is dq, upon Z square plus X square, and this direction is in the r cap direction. So let's say my dAe vector is if this is the r cap direction, so this direction is r cap. So r cap. So this is my electric field at point P due to a wire that is wire on which a charge is distributed along a line, and we have the linear charge density lambda. So what I can see is that if this angle is theta, so if I extend this line and draw a horizontal line over here, then this angle is also equal to theta. And I can see my DE has two components. So DE cos theta minus I cap, and along minus x, and DE sin theta along k cap. Okay, so and the wire is kept along x and y is outwards. Okay, so along plus z. So this direction is z and this direction is x. So I'll consider one component at a time. So let's consider dE cos theta. So dE cos theta is equal to lambda dx upon 4 pi epsilon naught under root z square. Okay, this is square. So z square plus x square square into cos theta, and the value of cos theta is x upon under root z square plus x square. So my dE cos theta, this is along minus I cap. So this is dE x. Okay, so this is lambda dx x upon 4 pi epsilon naught z square plus x square to the power 1 by 3 by 2, because 2 plus 1 by 2 is 2. This is square, so this is 1, and this 1 plus 1 by 2 is 3 by 2. Okay, so this is along minus cap. Okay, so my dEx is equal to this, and if I integrate it on the both side, I'll have Ex equal to integration lambda dx x upon 4 pi epsilon naught z square plus x square to the power 3 by 2 along minus I cap. Okay, so to solve this integration, what you can do is you can take z square plus x square equal to t, and then my 2x dx is equal to dt, then I can replace my x dx by dt by 2. So I'll have dt by 2, and over here we have 4 pi epsilon naught, and in place of z squared plus x squared I can write t to the power 3 by 2, and my integration when my variable is x goes from 0 to L. Okay, so if I change my limit over here, so my limit will be uh, this will be x will be t square. So if my x is equal to 0, then my t is equal to z square, and if my x square is equal to L square, then this will be equal to z square plus L square. So what you can do is now just take it in the denominator and apply the simple integration formula for nth power and can solve it. So this will be the component along minus I cap. So similarly, what you can do is you can calculate the electric field at point P due to the vertical component. Okay, so the vertical component is dEz, which will be equal to 1 by 4 pi epsilon naught lambda dx upon z square plus x square, uh, 1 by 2 square sine theta, and sine theta is now equal to lambda dx upon z square plus x square to the power 1, and sine theta can be replaced by z upon x z square plus x square to the power 1 by 2. So again this will be 3 by 2, and you can solve this integration by putting x square equal to z squared, x square is equal to z squared tan square theta. Then you can take z square out of the bracket, and inside this bracket we will have 1 plus tan square theta that can be changed to sec square theta, and accordingly you can change dx to in terms of theta. So that's how you will do this integration if you will integrate it on the both side. So in general, this is how we have to evaluate the field at point P due to a wire or a distribution where a charge is distributed along a line. Okay, so I'm not doing this question in full detail. The integration is part is up to you, and we will discuss another problem in which the charge is distributed along on a surface. Okay, we will try to solve or try to evaluate the field generated due to 2-point charges. So suppose that I have two charges plus q and minus q, which are a distance apart, and I want to calculate the electric field at a point P, that is z above this z above from the midpoint between these two charges, and I want to calculate the field at point P. So evaluate the field at point P. First, I have to see what is the electric field due to these individual charges. So plus Q. So plus Q. So a plus Q charge always generate a outward field. Okay. So and a minus Q charge always generates an inward field. So we'll use this concept. So plus Q will always generate an outward field. So an outward field at point, so let me take this pic to over here. So over here, okay. So if I try to evaluate my field at point P due to these individual charges, okay, so calculate the field at point P due to these individual charges. So if I consider my charge plus Q first, the field at point P due to this charge is outward from here, and the field due to the minus Q charge will be inwards, that is towards Q. This is due to E due to plus Q, and this is E due to minus Q. Okay, so if this angle is theta, this angle is theta, this is 90, this is 90. So then this angle is 90 minus theta, this angle is 90 minus theta. Okay, so then this is 90 minus theta and this is 90 minus, this is equal to 90 minus theta, and this is 90 minus theta, so this is theta, and this is equal to 90 minus theta, 90 180 minus 2 theta, so this is theta, and this is also theta. Okay, so 90 minus theta plus theta is equal to 90. So is equal to 180 degrees. So it's a linear pair. So our answer is right. So if I try to find the field at point P due to these two charges, so what I can see is that I have two components. So my E plus Q cos, so E plus Q sine theta is upward here, and E minus Q sine theta is here, and at this point my components will be E plus Q cos theta and plus E minus Q cos theta. Okay, so as I can see that at point P the vertical component are equal and opposite. So let's calculate E plus Q. So E plus Q is equal to Q upon 4 pi epsilon naught, and if this is A, this is Z, so this is equal to A by 2 square plus Z square. Let's call this distance equal as R. So this is equal to R square. Okay. And similarly for E minus Q, my field is Q upon 4 pi epsilon naught R square, since this distance will also be equal to R equal to A square by 2 whole A by 2 whole square plus Z square. Okay. So as I can see, the vertical components are equal and opposite. So these two components will cancel out and my answer will be E plus Q cos theta plus E minus Q cos theta. Okay, so if I substitute the values for the field for each and every charge, it will be equal to 2Q by 4 pi epsilon naught R square cos theta. So this is equal to E vector So this is equal to E total, that is the field due to equal and opposite charges which are kept a distance apart, and the direction of the force is along x cap. So if I try to write this field in terms of the vector, this will be equal to x cap. Okay, and cos theta, as you can see from the diagram, is equal to a by 2 upon under root a by 2 square plus z square, and r square is equal to a by 2 whole square plus z square. So you can substitute all this value and you can calculate the magnitude of the electric field at point P due to plus q and minus q charges, and the field due to both these charges will be along the x cap and the vertical component will cancel out. So you see how we can solve the elementary problem in electrostatics by considering the field due to individual charges. So in actually we are just applying the superposition principle in which we are calculating the field at point P due to each and every charge that is present, that is under consideration. So in our consideration we have a plus q charge and a minus q charge, and we have calculated the field due to these individual charges and calculated the field at point P. So now suppose that at point P I have a test charge capital QT. So if my QT is capital is test charge, so if I need to calculate the force at point P due to this two charges, what I can do is I have to just multiply it by this field, then I will have the magnitude and the direction of the force on the test charge due to this two charges plus q and minus q. So you can see we are just applying the superposition principle that we studied in the previous lecture. Okay, so now let's move to continuous system. So suppose that rather than having discrete particles, so rather than having discrete particles like q1, q2 to qn, so these are my discrete particles, that is I can count them, and I have another test charge qt. So rather than having discrete charge particle, I have a continuous charge body. So if rather than having discrete charge particle, I have a continuous body that is fully charged, and I have to calculate the force on the test charge due to this continuous charge body. So how do we have to calculate the force? So to calculate the force due to the continuous charge body, you have to use calculus. Okay, so let's take an example. So I'll not draw coordinate system again and again. So let's suppose that if point O is my origin and I have a continuous source charge, okay, and I have a test charge qt, or we want to calculate the force on the charge qt that is at point P, and or the field at point P. So the position of the source charges are, Okay, so if the position of the source charges are and my position vector of the test charges RT, then how do we have to calculate the force due to this continuous charge system? So what you can do is, let's consider a differential charge dq, that is a small volume. Let's say the volume of this small block is dv. Okay, so dv is the small volume. Okay, and suppose that the charge per unit density is rho. This is charge per unit density. So charge per unit density is how the charge is distributed in this continuous charge source. So if I want to calculate the charge in this system dV, it will be equal to rho dV. And if I have to calculate the field at point P due to this point charge, due to this continuous source charge, if I take my origin, if this is equal to Rp and this is equal to R, and this will be equal to R dq, and this is equal to R. So what I can do is, now I have to evaluate rho dv by r square. So this will be a triple integral because we are calculating the integration over a volume. So if I need to calculate the field at point P along r cap, so this is equal to r. So if I need to calculate the electric field at point P due to the continuous source charges distribution, then I have to evaluate this by using this formula. And suppose that if my, rather than having a continuous volume, a bulk volume, we have a surface charge distribution sigma, then my electric field at point P will change to 1 by 4 pi epsilon naught sigma dA upon r square. And if my source charge distribution is along a line, so in that case I have lambda, that is the linear charge density, that is how the charge is distributed along a line. In that case my field will be equal to 1 by 4 pi epsilon naught lambda dl upon r square, and the field will be along r cap. So this is how we have to calculate the field at point P due to continuous charge distribution, and we will learn how to calculate field due to by using this formula or this notation. So by using this integration, we will learn how to calculate the field at point P or at any point due to this system of charge particles. And this is not a system, this is a system of charge particle, but it's not a discrete distribution but a continuous distribution. So that's why my summation will change to integration. When I move to discrete to continuous, my summation will change to integration. Okay, so these are the formula for calculating the field. So let's move to other topics in electrostatics.